of functions. Guys, what does first derivative tell you about functions?
The slope of
Yeah, rate of change, slope,
Yeah.
you bet. Okay. So today we're going to start looking at what it means to not work with just a first derivative, but look at the second derivative. And what we're trying to answer today is the following: what does the second derivative tell us about functions, and how can it be found? Okay. So goals today, we're looking to understand concavity of graphs. You guys remember talking concave up and concave down?
Yes.
Remember when I said if it's shaped like a cup, it's concave up. Shaped like a cup, it's concave up. If it's shaped like an umbrella, then it's concave down. Okay. So we're going to try and understand that concavity of graphs again. We're going to apply the second derivatives to position functions to find acceleration. We're also going to look to determine signs of second derivatives. We're going to estimate second derivatives from tables. And we're going to interpret information about the second derivatives from graphs. Now guys, it sounds pretty impressive, but I have to be honest with you. Of all the sections that we've done so far this trimester, I think that this might be one of the easiest ones. Okay. So let's get some vocab behind us here. First one is concave up. I have a volunteer that would read concave up.
Interval on graph where the rate of change of the rate of change is positive.
Whoa. Rate of change of the rate of change is positive. Okay. We have spent a lot of time looking at slopes. Okay. But we haven't talked much about how is that slope changing over time. So concave up kind of means this, kids. First of all, just pick a point like this and make a graph like this. Guys, is my slope increasing or decreasing, first of all?
Increase.
Okay, so listen to what I say here. Talk to me about these slopes as I move from left to right. Are the slope values going to be changing for higher values, or are they going to become less and less? In other words, my slope right here is positive. The graph is increasing. But what's happening to my slope values as I move right? Is this getting steeper or less steep?
steeper.
So my slope values would be going up, wouldn't they? Okay. So when we talk about this definition of rate of change, they want to know what's happening to the rate of the slope. Is the rate of the slope getting steeper or less steep? Does that make sense? But now you have to think about them in terms of values, because like this, I could come down here like this with negative slopes. Guys, this is very steep negative, right? But as I go from steep negative slopes and flatten out down here to zero, thinking of slopes in terms of values, isn't zero slope going to be bigger than a negative slope? So as this bends around here, that slope is actually doing what? Well, it is increasing, okay? If you can think of, I don't know, maybe a line. Maybe this is the best way to show it to you. Here's a line right here, okay? Increasing. Okay, this becomes concave up because if I bend this up, the slopes are getting steeper and steeper, right? What would happen if I said, well, this is increasing, but I bend it down, kids? What kind of concavity is that? Concave down, okay? Let's talk about negative slopes. Okay, moving left to right, if I bend this up at the end here, that would be what? Okay, what if I bend the bottom down? Concave down, okay? So if you can think of moving left to right, if the graph is bending upward, anyhow, it's concave up, or if it's like this, okay? Think concave up, and it's bending down, be concave down here. So guys, notes to make over here about concave up. It's the interval on the graph where the rate of change is positive. Okay, concavity has everything to do with the second derivative. I'm going to make a note right in here. A graph is concave up for any x value if f double prime of x is greater than 0. Okay, you'll want to write that down. We'll see more of this in the notes as we move through this. Okay. Well, guys, if concave up means that the graph is going to be bending upward or slopes are going to increase, what do you think is going to be true of graphs that are concave down? The rate of change is going to be what?
Negative.
So in other words, I might have something like this. It's increasing, but what's happening to my slopes? Are my slopes getting bigger or smaller?
Smaller.
So as the slopes get smaller and smaller and smaller, you create a graph which is concave down. And as I relate that to second derivatives, for any x value where f double prime of x is less than 0, you would have a graph that's concave down. Okay. Now guys, you're also going to talk about points of inflection. And a point of inflection is a point where your concavity changes from up to down or what?
Down.
Okay, so as an example, let's just say, so you guys agree with this graph so far is concave what? Down. But right about here, this might start bending upward again, or the slopes start rising. Okay, this point right here where I go, I'm just make a big dot right about in there somewhere. Okay, my graphs started out positive, they flatten out, they go negative, my slopes are decreasing. But here, all of a sudden, my slope isn't as negative. It starts to flatten out towards 0 and then move back around towards positive. So the graph starts to show signs where slopes are increasing. So that point where we transition from concave down in this case to concave up, that's called my what? Point of inflection right here, okay? And at a point of inflection, kids, f double prime of x is going to be equal to 0. Reason it's 0 is because we transitioned from a situation where we were concave down, f double prime of x is negative, to concave up, f double prime of x is positive. To go from a negative to a positive, what value do you have to transition through to make that happen? 0. Okay. And then the second derivative we've kind of talked about, it's a derivative of a derivative. So if I had a function f of x, kids, and I said sketch f prime of x, you know how to do that, right? Okay. Then if I said sketch the second derivative, well, the second derivative is just the derivative of the first derivative, right? Second derivative is like the rate of change of the first rate of change. And that's all going to deal with concavity, how quickly slopes are changing. So in order to find the second derivative, we must first find what? First derivative. Okay. All right, terms-wise, are we okay on that? All right. Terms-wise, we should be okay. All right, well, then on the next page. Start talking about signs for second derivatives. It says determine whether the second derivatives are either positive, negative, or 0. So we just got done saying if it's concave up, second derivative is positive. If it's concave down, second derivative is negative. And if the second derivative is ever equal to 0, you are at a point of inflection. Okay? Let's move left to right on this. Kids, from left to right, is this concave up or down? To start.
Up.
Concave up right here, right? Does it transition to concave down?
Yes.
All right, I'm going to run right around here. You tell me when to stop when it goes from about concave up to concave down. Right here is where you want me to stop? Looks like now, guys, my slopes are starting to flatten out again, okay? So I'm not as steep. Again, I got to a 0 slope down here at this valley. Increasing slope, increasing slope, increasing slope. And now my slopes are still increasing, but they're starting to do what again? Speed up or slow down? Slowing down, okay? So the rate of change of those slopes is getting less and less and less, which indicates to me that's where the graph is concave down, okay? So on that second one, you put arrows in where you think the graph is concave up and concave down. And then we'll come back in and talk about where the second derivative is positive, negative, or 0 at, okay? So put some arrows in for concavity in that second graph. Don't worry about the third one yet. How's the graph start in that second one? Up or down? Down. Does it ever go up? Okay, so it's concave down in this part, concave up here, concave down there. Would you agree with that, kids? Okay, let's go back to the first one. I think it's important that when you have a point of inflection, divide your graph like this. Anywhere where you have a point of inflection, the second derivative is going to equal 0 at a point of inflection, okay? So meaning in this interval right here to the left of my dotted line, kids, what am I going to say about my second derivative for my graph here? Positive or negative? It's concave up, therefore positive. These really steep negative valued slopes are starting to flatten out to a 0. So that indicates to me the rate of change of the slope is increasing. So in this first interval over here, f double prime of x, positive. How about over here on the right? F double prime of x down here would be negative. Okay. How many points of inflection did you have on the second one?
2.
2. Do you guys agree about here, where it changes from down to up, and then maybe right about in here, where it goes from up back to down?
Yeah.
Okay. So right here on these dotted lines, that's where f double prime of x is equal to what, kids?
0.
Okay, so for these two right here, f double prime of x. Okay, is it positive or negative here? Okay, f double prime of x is negative here. How about here?
Positive.
Positive. How about here?
Negative.
Negative. Okay. Does this idea of concavity and second derivative science, is it clicking for you right now? Yes? So I have a question right here on the third one. We know where stuff is positive and negative or 0 at, but guys, how about this next one? Is that concave up or concave down?
It doesn't have any.
It's neither concave up nor concave down because the slope never ever does what?
Change.
It never changes. Therefore, it means f double prime of x everywhere should be what?
0.
0. Okay, anything that's linear, guys, anything that's linear like this will always, always, always be equal to 0. Okay, and let me tell you why. Guys, this function right here, could I come up with a function in slope-intercept form for this? Looks like the slope is what, down 2 and over 1, is that right?
Yeah.
Watch this right here. Do you guys agree that f of x up there is equal to negative 2x plus 3? Would you agree with that? Help me with the first derivative of this, kids. This linear function, first derivative. By power rule, or the rules that you know about slope-intercept form, what's f prime of x equal to?
Negative 2.
Negative 2. And then what's the second derivative going to be? What's the derivative of any constant all the time?
0.
For every x right here, we're saying it's equal to what here?
0.
Second derivative everywhere will be equal to 0. Indicating to be no concave up or no concave down part there. Okay? That makes sense? All right, let's rock. Kids right here. I'm going to plot these points in decimals real quickly. I'm going to kind of plot this here and see what our graph looks like just by points. So you guys help me out with this, okay? I'm going to go to decimals here. I need to know the values for my points if you'll give me a second, okay? I want to talk about what this looks like visually, talk about our slopes, talk about our concavity, and see if what we get in this problem justifies what we see. Oh, what do I want here? Decimals, right, kids? Decimals. The beautiful free math calculator. All right. I need those points. 0, comma what, kids?
6.9.
0.
0.2, 6.3. 0.4, 6.3. 0.6, 7.1. 0.6.
Oops, yeah, that's going to be a problem, isn't it?
0.8, 7.6. 1 is 7.7.
Let me make this fit. Is that okay? All right, kids, if I can draw a curve to this. Guys, if I could draw a curve to fit those points right there. Looks like to me this graph starts out by decreasing, comes back to increasing, right? Okay. Now guys, how about the concavity here to begin? Maybe the first half of the graph.
Concave up.
Looks like it's concave up, meaning my slope starts out negative, it flattens out to a 0, and then goes positive. So tell me about the slopes as we progress. Are the slopes increasing or decreasing? Which would indicate concave up. But I get to right about, do you guys agree about this 0.6 here? 0.6 relative to what point again, kids? 7.1? About this point, 0.6, 7.1, looks like it starts curving back down. My slopes are still increasing, or I'm sorry, my graph is still increasing, but what's happening to the slopes as I move from that beyond? They're starting to flatten out towards 0 again. They're decreasing, which would indicate where the graph is concave down. So just taking a look at this, kids, what's that even say there?
Use a flying table to estimate.
F double prime of,
0.8.
guys, do we think F double prime of 0.8 to even begin with will be positive or negative? Okay, F double prime, second derivative, works with concavity. So at 0.8, I'm not worried about the slope anymore. What I am worried here is at 0.8 right here, is this concave up or concave down? So F double prime of 0.8 should be what type of value when we're all done? Negative. Yeah, visually this is what our points look like. So let's see if that's true. Let's see if that's true. Let's, we're only going to find this for F double prime of 0.8, right? So let's do this. Let's find F prime at 0.8. So I'm going to work backwards. I'm going to use these 2 points as my interval. Is that okay, kids? All right. Help me out, guys. So maybe F prime of 0.8 right here. I would take 7.6 minus what, kids? 7.1. Okay, so this would be 7.6 minus 7.1 over 0.8 minus 0.6. Somebody run that for me. 7.6 minus 7.1 over 0.8 minus 0.6. 2.5. Okay. Now guys, I have a question for you. This is the box I'm really worried about right here. I want to find F double prime of, or estimate I guess I should say, F double prime of 0.8. Okay. I need to know this value right here. Well guys, I can't find that unless I know two values up here from F prime of X. So I'm going to come back here in blue and I'm going to say, let's use, hang on a second. I'm going to say, let's use 0.4 to 0.6 right here to estimate, gosh darn it. Let's use 0.4 to 0.6 to estimate a slope here. So somebody go 7.1 minus 6.3 and then 0.6 minus 0.4 in the denominator. So what is it, 0.8 over 0.2? 4. Okay, so we think a good F prime of X at 0.6 is 4. Guys, talk to me about F prime of X from 0.6 to 0.8. What's happening to my slope values? Even though both slopes are positive, they're decreasing, okay? So now, kids, what we can do is we can find a value for F double prime of 0.8. And this is how we do it. We go do the derivative of the first derivative. So I would take now 2.5 minus what, kids? 4. What is 2.5 minus 4? Take that negative 1.5 and divide it by that interval we're working with, 0.8 to 0.6. So take that negative 1.5 and divide by 0.2. Kids, I have a question. That second derivative at 0.8, at negative 7.5 indicates to me that the slopes are decreasing, which would mean the concavity of the graph is concave down there, okay? And guys, doesn't this numerically justify what we saw? Oh, did I get rid of that? I must have. Did you remember that graph that we had up there? Okay, doesn't that numeric value of negative 7.5 justify what we thought? We thought it was going to be concave down there, didn't we? Okay, and that's what this justifies. So guys, If I would ask you to fill in the rest of this table, do you think you could do it? Figure out all your slopes right here and then use this row right here to calculate your bottom row. Okay? All right, questions so far? I know I'm going quickly, but I kind of believe that this makes sense. Let's talk. At the top, this is a pretty important example. I want you to not worry about so much about what's up here. Okay, don't worry about what's up here. What I do want to worry about is this graph right here. I'm going to tell you this graph here is f of x. Okay, that graph is f of x. So, on that graph, I have some points, A, B, C, and D. Guys, take a look at B closely. I don't think B is completely at the peak, do you? So, do you guys think this, you think it's a little left of the peak?
Yes.
Okay, so, but what about A being in a valley? Are you okay with that? Okay. They ask you some questions about this table right here. They say I have this graph with points A, B, C, and D defined on function f. And what they want to know is, are the following signs, give the signs of the following. Are they positive? Are they negative? Or could they be what value?
Zero.
0. Okay. So first column says identify f right here. What would you say about point A? What is f?
Looks like it's in a valley,
So you're saying what?
Oh, okay, wait. Negative.
Why negative, Kylie?
Because the point is like it's
Below that.
Below the x-axis, absolutely. If you give, if I give you an initial function, okay, and they start asking you questions like this, give the values or the signs of f. F is always kind of like saying, what's the value of it? Is that value positive, negative, or 0? Well, since A lies below the x-axis, it must be what?
negative.
Okay, what's that make B and C?
Positive.
They're both above. What's that make D? Absolutely. Okay. So here's f of x, it's sitting there. Now they go on and say, what's true about the values of f prime of x? And you're like, well, if I'm given f of x, then f prime of x is talking about everywhere wants to know if the slope is positive or negative. Okay? Well, talk to me about A.
Now it's 0.
Now it's 0 because that's at a valley. The rate of change down there is 0. Okay? If I drew a tangent line to this right here, wouldn't it be horizontal, kids?
Yes.
And the slope of that horizontal tangent would be?
0.
How about B? We think it's just to the left of that peak,
Positive.
so it has to be positive. Talk to me about C.
Negative.
Yep, it's decreasing. Negative slope. Talk to me about D. We're back to positive. Okay? So guys, if F talks about what's the value, and F prime talks about the slope, then what the heck is F double prime wanting to know?
Whether it's in concavity.
Yep, it wants to know all about its concavity here. So guys, look at your point A. Concave up, concave down, or point of inflection.
Concave up.
So it would be positive, right? How about B and C?
Down.
Definitely concave down, so F double prime at B and C would be what?
Negative.
Absolutely. What's D going to be?
Positive.
Positive. It's concave up there. Okay? Doable? How do you feel about this? Not too bad, is it? Okay? Questions to this point? I think if you can understand this table, you're in great shape, okay? All right. Graphical reasoning. Tests on a C5 Chevrolet Corvette sports car shown below. Talking about its velocity over time. At time 0, I haven't timed anything because the car hasn't started doing what?
Moving.
So at time 0, it's going how fast?
0.
At time 3, how fast is it going? At time 6. At time 9, it's 43, and time 12 is 51. Guys, talk to me about the spacing of t. Consistent or inconsistent?
Consistent.
Yeah, it goes up by 3 each time, all right? Talk to me about the velocities, increasing or decreasing?
Increasing.
Listen to what I say. Talk to me then about the rate of change in my velocities.
Positive.
The rate of change of those, the rate of change in those, it is positive, but, well, I think we better take I think we better take a look at this.
It's going up less each time.
Yeah, okay, so in other words, it's accelerating slower and slower and slower, okay? The rate of acceleration is a little bit slower. Here, guys, it says estimate dv dt, or the derivative of v with respect to t for the time intervals. Let's just put that right down here. Okay, for the first one right here, we would have, what's the change in velocity, kids?
20,
Divided by what?
3.
3. 20 divided by 3. 6 2/3, is that right?
Yeah.
Okay, that's the first change. Next one then. 13 over what?
3.
Which is what? 4 2/3? 4 1/3? Okay. Let's do the next one, which is 3 1/3. Last one. So guys, what this is telling me right here is this. We're saying, yes, my velocity over time is increasing, but the rate at which that velocity is changing is actually doing what? Speeding up or slowing down? Okay, so the question says this. And this, if you can imagine this, my velocity time graph looks kind of like this. At time 0, it starts out 0, it takes off, but my increasing velocities aren't increasing as quickly. They're starting to level off, aren't they? Or these values that start at 6 2/3 is now down to 2 2/3. So the question down here says, what can you say about the second derivative of this function over the interval?
It's concave down.
It's concave down, which means the second derivative everywhere would be positive or negative.
Negative.
Okay, since, is it okay to say this? Since my slope values, my slope values all positive, but moving from left to right on my slope values, what are they doing? Increasing or decreasing? So I'm going to say since the slope values are whoops. Graph is concave down. Which means the second derivative of v, dv, 2 over, whoops. Which means the second derivative of velocity with respect to time must be positive or negative. Yep, the rate of change of the rate of change is decreasing. Guys, last thing I want to show you about second derivatives and how they relate to position, velocity, and acceleration. This is a pretty cool one. You guys have what you need there? Good? Okay. Right here, last one. Rules about position, velocity, acceleration. Suppose f of x is some position function. In other words, it's like a distance divided by time thing, or a distance time graph. So if I travel a certain distance over a certain amount of time, that represents a position. I might say in 1 hour, I've gone 55 miles. In 2 hours, I've gone 110 miles. In 3 hours, I've gone 165 miles. That's like saying how far I am at a certain time. You get that? That's position. Anybody know what f prime of x is then? If I would say maybe my distance is measured in miles and my time is measured in hours? Miles per hour, which is a velocity. So when we start relating position graphs or distance compared to time graphs, it turns out that the first derivative of any position graph is a velocity graph at a certain time t. Okay, and we'll talk more about this as we progress. Anybody want to guess what f double prime of x is then? It's acceleration, you bet. It's acceleration right there. So, just kind of have those in your back pocket. But kids, do you understand where graphs are concave up and concave down? Do you understand points of inflection? Okay. Do you understand how to find the second derivative given the table right now? Okay. I think you're going to be in pretty good shape here. So I'm going to go ahead and stop this right now.